This is section 10.2, Sum and Difference Identities. Okay, the first thing I'd like to do with you is to derive an identity for the cosine of the difference of two angles. And I'm going to use A and B as the angle names. I think you're probably going to be happy that I'm not using alpha and beta because you don't want to have to draw those alphas and betas all over the place, I'm sure. So let's just let that be A and B. All right. So what I'd like to assume is that I have angles in standard position. Let's let angle A in standard position, of course, one side is on the positive x-axis. And let's just say that A is over here someplace. Its terminal side is over there. And so this is angle A. And I want it to be relatively big compared to B because I'm going to subtract those two. So anyway, let's see. Let's say that B is one that terminates about right there. So that's angle B. And let's see, what do we want to do next? Well, if I were to draw a circle centered at the origin, you're going to have to pretend like this is a circle, because obviously I'm not drawing a perfect circle. Pretend like that's a perfect circle centered at the origin. And furthermore, let's say that the point right here, P, is at 1, 0. And what that means is that when the radius of the circle is 1, we call this a unit circle. And something that's true about the unit circle that we haven't discovered yet, but I'd like to go ahead and introduce it to you now, is that we know that, for example, the cosine of theta, where theta is just the name of an angle, is the definition in terms of x, y, and r is x over r, right? But if r is 1 for a unit circle, cosine of your angle is the x-coordinate of that point. So that means that this point right here, if I call it Q, the x-coordinate is cosine of the angle that produced that. And of course this one is B, so this is cosine B. Okay, so what's the definition of sine of theta in terms of x's and y's and r's? Well, it's y over r, and if we have a unit circle, meaning the radius is 1, that simplifies to be y over 1 is simply y. So that means that the sine of the angle in a unit circle is the y-coordinate of that point. So that means that the y-coordinate of point Q is the sine of the angle B. So what are the coordinates of this point, which I'm going to call S? What are the coordinates of that point? Well, it's still on a unit circle, although my circle doesn't look very circular. It's supposed to be, and so it's going to be, the x-coordinate will be cosine of the angle, and that's cosine of A, comma, and the y will be sine of the angle, so that will be sine of A. That's the coordinate of that point there on the circle. All right. So, if we were to subtract a minus b, how big would it be? Well, a minus b would go from the green to the pink, right? And so, let me pick a color for this. Let's do that color. A minus b would be from here to here. But what I want to do is I want to rotate it so that it's in standard position. So what I'm going to do is I'm going to rotate it down so that the green is on the positive x-axis, which means the pink is going to rotate around a 2, the exact same amount. And let's just say that, let me erase what I just did. That arc is what we're trying to repeat, but I'm going to erase it because it will kind of get my way. So let's just assume that I'm going to take B away from A, which is going to put it about right here. This is what A minus B would end up at, let's say. And so there is A minus B in standard position as an angle, A minus B. Okay? And what are the coordinates of that point, which we can call R? Well, it's going to be cosine of the angle, cosine of A minus B. Oh, yippee, we're finally getting to one of the things we're looking for. Cosine of A minus B right there. And the y coordinate will be sine of that angle, sine of A minus B, are the coordinates of that point on the unit circle. Okay, so how does that help us? Well, the picture's getting awfully crowded. What I'm going to do is I'm going to recreate only part of it over to the side, the part that I want to highlight. So I'm not changing anything really. I'm just taking away some of the clutter. Not meaning it's unimportant. It just is more than I want to have on this picture so that you can see things better. So let me draw things in. Oh, rats. I want it to look the same. Let me try again. Oops. Okay. So I'm just drawing the terminal sides because all the initial sides are on the positive x-axis. So here's that. And I'm going to call that S, that point right there. The coordinates of it are over to the left, but just look there. Let me see. This one, terminal side, and let's call that point R, and its coordinates over there to the left. And the green is about there, and that's point Q, and the point P and its coordinates over there as well to the left. Okay, so those are the 4 points. And what I would like to suggest to you is this, that between the green and the pink, that the angle between that is the same as from the angle from P to R. And so if I were to draw a dotted line from S to Q, and if I were to draw a dotted line from R to P, because the angles, which are called central angles, the angles are the same size. A minus B is the angle that produces the yellow one, and A minus B is also the one that produces the purple one. They're the same length. Okay? So those chords, the purple chord from S to Q and the chord from that's in yellow from R to P, those are the same length. Okay. So my conclusion would be that the chords PR and SQ are equal. Okay, so to find the length of a chord, that's the distance between 2 points in the plane, I can use the distance formula. So if I want to start with the idea that chord PR, oops, I'll write the P first. PR is the same length as SQ. Then I can find the length of PR using the distance formula. So we're going to use the coordinates for P and R. So R is the cosine of A minus B, sine of A minus, those are the X and Y coordinates for R. So that's going to be X sub 2, which is the R's X. So cosine of A minus B minus X sub 1. The X coordinate for P is 1. So X sub 2 minus X sub 1 quantity squared plus Y sub 2, which is sine of A minus B, that's the Y coordinate of point R, minus Y sub 2, 0. 0 is the Y coordinate of point P, quantity squared. And then SQ, I'm going to do the same thing. I'm going to write the distance formula from S to Q. So X sub 2, the X for point Q is cosine of B minus the X coordinate for S is cosine of A, quantity squared, plus Y sub 2, which is sine of B, minus Y sub 1, which is sine of A, quantity squared. And that's still under the radical. Okay, then there's all kinds of algebra now that I'm going to go through, and I'm going to go through it kind of quickly. Not that I ever want you to be able to reproduce this argument. I just want you to realize that the identity I'm about to derive is derivable, maybe not by you. If you had to do it all by yourself from scratch without much help, that would probably be a pretty hard task, and that's not something I'm going to ask you to do. But I want you to follow along and kind of nod your head and feel like, yeah, I understand what he's saying. Now, I don't think I would have thought of that myself, but I get it. And follow along so that when we're done, you are feeling confident that I've proven the identity. And this is not, again, not something I would ask you to do. So what I'm going to do is I'm going to start by getting rid of the radicals by squaring both sides. I'm going to do a little simplification. Sine of A minus B minus 0 is still sine of A minus B, and that will be squared. So sine squared of A minus B. And that would leave what's under the radical when I square both sides of the equation. Okay. So let's see. Let me do the squaring. You should know how to square a binomial. In general, this is what it would look like. This is one of those algebraic things you're supposed to know how to do. A plus b squared is the square of the first thing. Keep the sign of the middle thing, so plus. Then 2 times the product of the two items in the binomial, so 2 times ab, plus, and then finally the square of the second item. So if that ends up being a minus b that's squared, it's almost the same. It's the square of the first thing, keep the sign of the middle, minus, that's what's different. And then 2 times the first times the second, 2 times a times b, plus the square of the second. So I'm going to use that squaring idea very quickly here. Squaring cosine of something minus 1 will give me cosine squared of a minus b minus 2 times 1 times cosine of a minus b plus 1 squared is 1 plus then the sine squared of a minus b, which I just copied from above. Okay, I'm going to do the same thing on the right side. I'm going to move over here because it's way too long to write. So the right side is now down here. That will be cosine squared b minus 2 cosine a times cosine b. You may wonder about the order in which I wrote those. All I'm doing is I'm putting, it really should have been 2 cosine b cosine a technically, but I'm kind of ordering the angles alphabetically. And of course, when you're multiplying 2 times 7 and 7 times 2 are the same thing, so I can commute cosine b times cosine a to be cosine a cosine b plus cosine squared of a plus, and then squaring the other one, that will be sine squared b minus 2 sine b sine a. And again, I'm going to put those more or less in alphabetical order. So I'm going to write sine a sine b instead of what I originally said, plus sine squared of a. Now, here comes the fun part of this. I see cosine squared of something plus sine squared of that same something. And so that's going to give me 1. Plus this 1 right there makes 2 on the left side. Minus 2 cosine of a minus b. Okay, that's the left-hand side. Okay, next fun thing. I see cosine squared b on the right, and I see plus sine squared b on the right. That adds up to be 1. Then furthermore, I see cosine squared a plus sine squared a. That's another 1. So that's 1 plus 1 is a total of 2 from those underlined things. Okay, minus 2 cosine a cosine b minus 2 sine a sine b. Okay. All right. So one thing I see is that I have 2 on both sides, so I'm going to subtract 2 from both sides, leaving negative 2 cosine of a minus b equals, and that first 2 is gone, negative 2 cosine A cosine B minus 2 sine A sine B okay. Then I'm trying to get cosine of A minus B all by itself. So what I'm going to do is I'm going to divide both sides of the equation by negative 2. Which leaves cosine of A minus B, which is what I was hoping for. And if you split that fraction, you'll have negative 2 cosine A cosine B divided by negative 2, which will simplify to be simply cosine A cosine B minus, and then you'll have 2 sine A sine B divided by negative 2, which will become plus sine A sine B. And that is the identity for the cosine of a difference of 2 angles. Okay, so that is an identity. It's a difference identity, or cosine of a difference. And that's the first one of those, and you need to memorize that. So commit that to memory. The identity, not the derivation of it, but the identity itself. Now, to find cosine of the sum, A plus B, we're not going to have to do all of that same stuff, thank goodness, because we can use algebra. I can rewrite cosine of A plus B as a difference. It's the cosine of A minus the opposite of B, right? Isn't that the same thing as A plus B? And using the identity we just learned, that's going to be cosine of the first angle. And by the way, this is how I say these on purpose so that it's a memory thing. I always say for cosine of a difference, it's going to be cosine of the first times cosine of the second, and the second one here is opposite of B. That's our second answer, plus sine of the first angle, so sine of A, times the sine of the second angle, which is opposite of B. Okay, now we're going to use our even-odd identities. The cosine of negative B is the same as cosine B, so this is cosine A cosine B, because it's an even function. And then sine of the opposite of B is going to be the opposite of sine of B. And if I pull that negative out in front of that product, it'll be minus sine A sine of B. And there's our next identity. This is the sum identity for cosine. The cosine of the sum is cosine of the first, cosine of the second, minus sine of the first, sine of the second. And in fact, you can say both of these in one way, and it's true for both. If you do cosine of A plus or minus B, it's cosine of the first, cosine of the second, change the sign. When it's A plus B, then the second box, it becomes a minus. Up above in that box, when it's A minus B, in the identity it becomes a plus. So I say cosine of the first, cosine of the second, change the sign, sine of the first, sine of the second. And that's the little memory thing that I do to get those in my head. So those are the cosine identities of sum or difference. Well, why do we want those? Why do we need those? Well, I'll tell you. If I asked you for the exact value of an angle that's not one of our special ones, remember our specials were the quadrantals, and anything that had a reference angle of 30 degrees, 45 degrees, or 60 degrees. And of course the radian versions of those. But here I want the exact value for something that's not in that list. Like, what's the cosine of 15 degrees? Exactly. Well, to do this, you're going to have to think, can I rewrite 15 degrees as the sum or the difference of two of the nice angles that I already know? So there are actually several options here. I'm going to use 45 degrees minus 30 degrees, which will work. There are other possibilities. The other good possibility is 60 degrees minus 45 degrees. And you can use other angles and other quadrants. It's just harder to work with them. So if I can stick with quadrant 1 angles, it makes my life easier. So I've rewritten 15 degrees as 45 degrees minus 30 degrees. That's now the cosine of a difference. So that will be cosine of the first times cosine of the second. Change the sign, so that becomes plus. Sine of the first angle times sine of the second angle. And those are all values at this point that you should know or be able to get very quickly. That's square root of 2 over 2. Cosine of 30 degrees is square root of 3 over 2. Sine of 45 degrees is square root of 2 over 2. Sine of 30 degrees is 1/2. Okay. So doing the multiplications, you get square root of 6 over 4 plus square root of 2 over 4. And to add those, luckily we already have a common denominator, so we just add the numerator, square root of 6 plus square root of 2, all over our common denominator, 4. So I challenge you to pick up your calculator now and type in cosine of 15, make sure you're in degree mode, and then type square root of 6 plus square root of 2, make sure you have that in parentheses, divided by 4, and those two decimal numbers should be the same. If we've done this correctly, that's the exact value of what cosine of 15 degrees is, and you can compare the decimal values for those two, and they should be identical. Okay, so let's do another one like that. Now, probably you didn't need these written down for the degrees, but the special angles that I'm thinking of that we already know the answers for are these. I'm going to write a few of them, not all of them all the way around, because that's just ridiculously long and not necessary. Okay, so that's a partial list of all of our nice angles that have a reference angle that's nice to work with. In radians, and this may be more important, they are 0, because I think you could think of the degree ones by yourself, but the radian ones you're not as comfortable with, I think. So let me write all of those in terms of radians, what those nice angles are. Let's see, pi over 2, 2 pi over 3, well, etc. You can go further if you need to. But we hope that the first quadrant angles will be sufficient, because it does make it tons easier if it's a quadrant 1 angle that you use. Okay, so the next problem is find the cosine of 5 pi over 12. So if the angle has a denominator of 12, what you may want to think of is, in terms of twelfths of pi, what are each of these? So this one is 0 pi over 12. This one is 2 pi over 12. You following what I'm doing here? The next one is what? 3 pi over 12, right? The next one, 4 pi over 12. Next one, 6 pi over 12. 8 pi over 12. Well, you get the idea. So not only do you need to know the special angles in radians, you might need to change the denominator so that you can work your problem. Because we're looking for two of those that would add or subtract to be 5 pi over 12. 5 pi over 12. Since the last one we did subtraction, let's try addition on this one. You could use subtraction again if you wanted to, but I want to change it up a bit. So do you see that that would be 2 pi over 12 plus 3 pi over 12? Right? Does that make sense? Okay. So writing those in reduced form so I have nicer numbers to work with, that will be the cosine of pi over 6 plus pi over 4. By the way, like other problems we see in math, this one could have been done with, say, for example, 8 pi over 12 minus 3 pi over 12. And we could have done it that way, and it would have been just fine. I'm trying to mix it up a bit so you're using different identities, but had you done the one I just mentioned with another one with subtraction, it would have worked out just fine. Okay, so anyway, the identity is cosine of the first times cosine of the second. Change the sign, so minus sine of the first times sine of the second. Okay, cosine of pi over 6 is square root of 3 over 2. Cosine of pi over 4 is square root of 2 over 2. Yes, these are things that you should know or be able to get pretty quickly. Sine of pi over 6 is 1/2, without a calculator, by the way. And sine of pi over 4 is square root of 2 over 2. So that ends up being square root of 6 over 4 minus square root of 2 over 4. They have the same denominator, so they subtract over the common denominator, 4. And that's my final answer for that one. Okay, now you may have heard me say at one point you need to know all of your basic identities forward and backward, and this is a good reason for it. If I ask you to find the exact value of cosine of 87 degrees multiplied by the cosine of 93 degrees. Oh, and by the way, when I say exact value, generally speaking, that means do not pick up your calculator. You shouldn't do it unless it's for simple arithmetic. You should not be picking up your calculator and typing this expression in. So exact value means basically leave your calculator alone. Okay, now I'm hoping that you see that this is the form of the cosine of a sum or difference, because I have cosine times cosine minus sine times sine with the same two angles used. The first angle is 87, the second one is 93. So if we use that identity backwards, this should be the cosine of the first angle, 87 degrees, then change the sign, plus the other angle, the second angle, 93 degrees. Then if you add those two, you should get 180 degrees, which is one of our nice quadrantal answers. And you should know that that's -1. Okay? And you should be able to do that without a calculator. All right. So let's do the next one. All right, so the next one that we're asked to do is to write cosine of 180 degrees minus theta as a trigonometric function of theta. So we don't want the 180 degrees minus, we just want a theta eventually. Well, using the cosine of a difference identity, that's cosine of the first, cosine of the second, change the sign, sine of the first, sine of the second. So the cosine of 180 degrees is -1 times cosine theta, plus the sine of 180 degrees is 0 times sine of theta, and that simplifies to be the opposite of cosine theta. Okay. Now, we're going to find the sine of a sum and the sine of a difference. So, first of all, I'm going to define the angle theta as a plus b. Okay, so just kind of take that as a given to get started with this next part. Okay, so I want to find the sine of a plus b. Well, I know one of our other identities we talked about, and I didn't review early on in the other section of identities, was the idea of the cofunction identities. So let me at least state what this is, at least for this, the one we need. The sine of any angle is equal to the cofunction of that trig function. The cofunction of the trig function will be the function we use on the right side, and what we're going to use on the right for the argument is the complement of that angle. And so the complement in terms of radians is pi over 2 minus that angle. Okay? That's the cofunction identity for sine. And all of them work that way. The trig function of theta will be the cofunction of that trig function of pi over 2 minus theta. And at the time, I believe we wrote 90 degrees minus theta because we were working in degrees. But I said at the time, too, that we could have replaced that 90 degrees with pi over 2 if we were working in radians. So this is the identity I want to use. I want to rewrite this in terms of cosine, in other words, the cofunction. And that's going to be pi over 2 minus whatever I'm taking the sine of. Notice the use of parentheses here. I'm subtracting whatever's the argument of sine, which is the sum a plus b. Well, I could distribute that subtraction if I wanted to, and write that as pi over 2 minus a, and then distributing, that's minus b. Then I could regroup and put the first two things inside of parentheses if I wanted to, and I do. So I now have the cosine of a difference of two things, where the first thing is a binomial. And we know the identity for cosine of something minus something. It's cosine of the first times cosine of the second, change the sign, sine of the first times sine of the second. Now, the cosine of pi over 2 minus a is using the cofunction identity, its cofunction, which is sine, of that A. So in other words, I'm kind of using this one in reverse, where theta is A. Okay? Cosine B. And then the sine of a complement is the cofunction of the original angle. Kind of the same idea, but with the other function, sine of B. And that is the identity for the sine of a sum. And what I say for this one, my little mnemonic, that I always kind of recite the same way, the sine of a sum is sine of the first, cosine of the second. Keep the sign. Notice the plus in the middle makes it plus over here. Okay, sine of the first, cosine of the second. Keep the sign, cosine of the first, sine of the second. And we could very easily find an identity for sine of A minus B. So let's do that. Sine of A minus B. We could rewrite that as the sine of a sum, A plus the opposite of B, and then use the identity we just learned. That will be sine of the first, cosine of the second. Keep the sign plus cosine of the first, sine of the second. So because cosine is even, cosine of negative b is the same thing as the cosine of b. So that's sine of A, cosine of b. And the sine of the opposite of b, since it's an odd function, is negative sine of b. Pulling that negative out in front, that'll be minus cosine A, sine of b. And so that is the identity for the sine of A minus B. Again, I'm going to say the exact same thing I said before. Sine of the first, cosine of the second one. Keep the sign, so minus. Then cosine of the first times sine of the second. Okay, so those are the sine of a sum or difference identities. I'm not going to prove this next one for you. I'm going to just ask you to believe me that the tangent of A plus B could be written as sine of A plus B over cosine of A plus B, and go through a whole bunch of substitutions and simplifications. And what that ends up being when you're done is tangent of the first, keep the sign, tangent of the second, tangent of the second one, divided by 1 minus the product of the tangents of the first and second. Okay? So that's the identity for tangent of a sum. In this section, if I put a box around it, it means you need to memorize it. The tangent of difference, therefore, is tangent of the first, keep the sign, tangent of the second, divided by 1, change the sign, so plus tangent of A, tangent of B. You can see that our number of trig identity has grown a lot today in this section. So you've got a lot of memorizing to do. So please, please, please do not put that off. Make sure you learn these as fast as you can. Okay, so we're going to use those identities now to find exact values for all of these problems. That is, basically, do not pick up your calculator, use the identities, and other things you know. So, part A, the sine of 75 degrees is what? Well, I need to think of two angles that add or subtract to be 75 degrees. Since 75 is not one of my special ones by itself, I'm thinking of 30 degrees plus 45 degrees. So I'm going to use the sine of a sum, which is sine of the first, cosine of the second, keep the sign, so plus cosine of the first, sine of the second. So sine of 30 degrees is 1/2. Cosine of 45 degrees is square root of 2 over 2, plus cosine of 30 degrees is square root of 3 over 2, times sine of 45 degrees is square root of 2 over 2. And so that ends up being square root of 2 plus square root of 6 all over the common denominator, 4. Okay, let's do another one. Move this over a bit. Go up some, move it over a little bit more so we don't see all that stuff over there. Okay, next one, B. Remember, these are exact. We're supposed to now find the tangent of 7 pi over 12. So I'm trying to think of two angles that are nice angles that add together to be 7 pi over 12. If you look at that list I wrote earlier of all the nice angles and then all of them in terms of twelfths of pi, that will really help if you kind of have those in your mind. What two could you add or subtract to get 7 pi over 12? Well, I was thinking 3 pi over 12 and 4 pi over 12 fits the bill quite nicely. And then writing those in terms of our more conventional versions of those angles. 3 pi over 12 is pi over 4. And 4 pi over 12 is pi over 3. Okay, so using the identity for tangent of a sum, it's tangent of the first, keep the sign, so plus, tangent of the second, divided by 1, change the sign, so minus, tangent of the first, times tangent of the second. Okay, so the tangent of pi over 4 is 1, plus the tangent of pi over 3 is square root of 3, over 1 minus tangent of pi over 4 is 1 times tangent of pi over 3, which is square root of 3. So 1 plus square root of 3 over 1 minus square root of 3. And then to rationalize that denominator, I need to multiply by a form of 1. The form of 1 I'm going to use is the conjugate of the denominator radical binomial. So 1 plus square root of 3 over itself as the form of 1. Doing the multiplication in the numerator, move this down a bit, gives me 1 plus 2 square roots of 3 plus square root of 9, which is 3, over 1 squared minus square root of 3 squared. So that's 4 plus 2 square roots of 3 over negative 2. If we split that fraction, that's 4 over negative 2 plus 2 square roots of 3 over negative 2. And so my final answer is negative 2 minus the square root of 3. That's that one. All right, for the next one, the question asks, for us to find the exact value of this expression, sine of 40 degrees, cosine of 160 degrees, neither of which is one of our special angles. That gives us a reference angle that's one of our nice ones, minus cosine of the same 40 degrees, sine of 160 degrees. Okay, so knowing the identities backward and forward is important. This takes the form of sine of a sum or difference. So this is sine of the first angle is 40, and then we keep the sign of the difference there between the two products, and then the second angle. And simplifying, that's the sine of negative 120 degrees, which we can very easily calculate without a calculator. That's negative square root of 3 over 2. And just a reminder of how you do that, in case it slipped your mind. First thing you would do is draw the angle standard position. So that far is 90. Need to go another 30 to get there. So that's my negative 120 degrees. Since I went an extra 30, that means that the remaining part to get all the way to negative 180 is a 60-degree reference angle. And if the reference angle is 60 degrees, the side opposite it is square root of 3. The short leg is 1, and the radius is 2 square root of 3. So x is in the negative direction because we're to the left of the y-axis, and y is below the x-axis, so that's a negative value. And remember, sine is y over r. So for this problem, that's negative square root of 3 divided by 2, which of course leads to our answer that we got. All right. Let's see what's next. All right, so next. Write the function as an expression involving functions of theta alone. Okay, so the first one is sine of 30 degrees plus theta. So using the sign of a sum, that's sine of the first, cosine of the second, keep the sign, cosine of the first, sine of the second. Okay, so sine of 30 degrees is 1/2, so that's 1/2 cosine theta. And cosine of 30 degrees is square root of 3/2 sine of theta. And cosine of theta and sine of theta are functions of theta alone, so we are in good shape and we're ready to go on. B, tangent of 45 degrees minus theta. Okay, we use the tangent of a difference formula. That's tangent of the first, keep the sign, tangent of the second, divided by 1, change the sign, tangent of the first times tangent of the second. So, tangent of 45 degrees is 1 minus tangent of theta divided by 1 plus tangent 45 degrees is 1 times tangent theta. And so we have 1 minus tangent theta over 1 plus tangent theta. Those are trig functions of theta alone, and so that is a good stopping point for that one. Okay, part C. Sine of 180 degrees plus theta. Using the sine of a sum formula, that's sine of the first, cosine of the second, keep the sign, plus cosine of the first, sine of the second. Sine of 180 degrees is 0 times cosine theta, plus cosine of 180 degrees is -1 times sine of theta. So our final answer here is the opposite of sine of theta. Okay. Let's see. I think what I'm going to do is close off this recording and start a part 2. So go on to the next recording now.